Hi everyone, I'm Yan, a PhD candidate from University of Massachusetts Law. Today, I'm going to present our paper, which is Imminence Monitoring of Critical Events, a representation learning approach. Our work is pioneering in applying the state-of-the-art representation learning to a novel data stream problem. I will talk about the details by following the outline, motivation, problem statement, solution, evaluation, and conclusion. First, let's talking about the motivation. Complex event monitoring is an important problem in data streams. For example, undesirable events in oil and gas wells. As another example, consider a hospital that has patients of serious diseases. The information is very heterogeneous. There are people of different ages and backgrounds, and there are many diseases and subcategories. Some urgent situations and events happen without well-known or uniform patterns to search for or to monitor. Nearly all work thus far assumes that the user knows and provides the complex event pattern to search for. However, oftentimes, we do not know the event or state transaction patterns to search for, but merely know that some interesting or critical events happen after the fact. To sum up, the pattern before the critical event is often subtle, complex, and not precisely known to users. It is difficult to use a simple language, such as variants of regular expressions, to express the pattern. There are deep learning approaches, such as LSTM. It's inflexible for continuous monitoring with different time intervals, and is about 2 orders of magnitude slower than our approach. To formalize the problem we are solving, here is the problem statement. We are given a period of history of a data stream. Some topes are labeled as critical topes, containing a critical event. Our goal is to learn a pattern that characterizes the sequence context with respect to critical event, such that for an unseen portion of a data stream, using the pattern and a continuous function, we can continuously monitor and predict how imminent the critical event is. In order to solve such problem, we propose a novel approach that uses relational machine learning and representation learning. We first convert the data stream to a dynamic knowledge graph. Representation learning of such dynamic knowledge graph. Then we propose novel event patterns by using probabilistic state machines. After all, we devise algorithms to measure the imminence of critical events using the probabilistic state machine patterns. Let me show how do we convert the data stream to a dynamic knowledge graph by an example. Here is a data stream, which is a real-life event log taken from the Dutch academic hospital. The log contains events related to the treatment and diagnosis steps for a heterogeneous mix of patients with cancer pertaining to the cervix, vulva, uterus, and ovary. Attributes include event name, treatment code, diagnosis, date and time, specialism code, activity code, department or lab, and age. We add an auxiliary node for each table called key node. The key nodes are shown as the hollow nodes in figure. Then we add an edge from key node to event node for each table's attribute, shown as the dashed edges in figure. The construction above, by using binary attribute relationships from key nodes to event nodes, preserves the original relationship among multiple event nodes of each table. We will create a number of states, and each table belongs to one of the states. To that end, we create a state holder node for each table. For each event node that the table has, we create an edge from event node to state holder nodes with a relationship and an associated attention weight. Finally, there's a special node called the critical state node, which is the state of all critical tables. Once we have the state holder nodes for each table, we create timing relationship edges such as followed by. These edges are the solid bold ones in figure. After we have such a dynamic knowledge graph, we are ready for representation learning. We need representation learning because we want to characterize the attribute correlations and the timing relationship between different type of states. In order to do so, we learn latent features for each vertex and the relationship type, together with the attention values of event state edges. The basic idea of our learning algorithm is to significantly extend trans-E, which is a translational-based embedding, to also learn the attention weights of attribute state edges. For some of you may not be very familiar with such topic, knowledge graph embedding is used to map each node and the relationship in a network to a vector in another multidimensional space. The basic goal is that if two nodes are similar or close in the graph, then the 2 points that they map to should also be close in that space. Trans-E is a simple and efficient one where the training tries to enforce the vectors satisfying H plus R approximately equal to T. Here is our loss function. The first sum in equation 1 is over a sample set of k even edges that contains both positive and negative samples. We obtain negative samples by corrupting either the head or tail of a positive trip in the sample set. For negative samples, the stochastic gradient descent will optimize the opposite direction, which is why we have the sum function, which return 1 if the triple is a positive sample and negative 1 if it is a negative sample. This part is same as trans-E algorithm. Similarly, the second sum is oversample over timing edges. The function basically returns either the embedding vector of the critical state node directly or the derived vector of the state holder nodes, which is the weighted aggregate of the tail ends of several even state relationships, where the weights are the attentions to be learned. We will get all vectors for nodes and the relations at the end. After we got those vectors, we are now ready to learn the probabilistic state motion pattern for the given critical event. The figure illustrates a probabilistic state motion pattern where we have 6 states, nodes A to F, and E is the critical state. The value on each edge is the transaction probability, while the vector next to each node is its embedding vector. The basic idea of the algorithm to learn a PSM pattern is that we first cluster the tubes in a stream window into a number of clusters, each of which will correspond to a state of the PSM pattern. There's also a special state, the critical state, corresponding to the critical event. Then the rest of the algorithm is mainly about estimating the probabilities of the followed by timing relationship between every pair of states through the embedding vectors we have learned. In order to monitor a substream, we first need to figure out what state we are in within the probabilistic state motion. This is not exactly trivial. Since data streams can be noisy or dynamic, then we need to monitor and foresee how imminent the critical event is. Therefore, we create a two-part cost model for it. First, the blending cost. Intuitively, it not only tells us how suitable the PSM pattern is for the given recent history, but it also informs us of the optimal estimate of the current state within the PSM. Then the projected future cost, upcoming information theoretic cost to reach the critical state. We use a history H over length H tuples to measure its minimum cost match with the given PSM. This can be done through dynamic programming over a breadth first search tree rooted at the current state. However, the numbers of choices at each state may be many, and the dynamic programming can be very expensive. We devised a novel A-star search algorithm to find optimal alignment between recent history and the PSM. By our design, in general, a transaction from state S apostrophe to state S occurs a cost negative log probability of S apostrophe S. Intuitively, if the transaction probability is 1, then the cost is 0. The lower the probability is, the higher the cost. We also consider cost of skipping a state in PSM or skipping events in history. We maintain a mean heap priority queue, and when expanding the search path, the algorithm explores all 3 plans and maintains the optimistic lower bound of future matching cost by summing up the match cost. And we also use our alignment algorithm to determine the optimal number of states in PSM. The second cost is the projected future cost to reach critical state. Let each directed edge I to j of m have information theoretic weight negative log probability ij. They run Dijkstra's algorithm and return the shortest path weight from the current state node to critical state node. The sum of those 2 costs is the total cost of the current trajectory to align and reach the goal. For evaluation, we use 4 real-world datasets and compare against 2 baseline approaches. The 4 datasets are hospital data, which is a real-life event log taken from the Dock Academic Hospital, an online grocery shopping dataset, a dataset of all taxi trips in the New York City in 2013, and a dataset of oil wells measurement events and undesirable real events. The 2 baseline approaches are IR-Manner, which is closest to our works, and RSTM model. We first evaluate and verify the efficiency and the quality of our continuous representation learning algorithm. Our algorithm incrementally updates existing embedding vectors as tuples arrive. Figure 3 and 4 shows that learning is very efficient, with throughput 3 to 5 times of that of the initial bunch embedding. But then also where the size of embedding vectors ranging from 20 to 100 and show the throughput results of the representation learning in figure 5 and 6. In both figures, the throughput slightly decrease as the size of embedding vectors increases, but the throughput of a continuous learning is 4 to 5 times than the initial bunch learning for the New York text data. Next, we evaluate the quality of our continuous learning. We examine how the loss function value in equation 1 that we optimize changes during the run of the algorithm. From the figures, it is clear that the loss function value of equation 1 decreases until it converges at a low value. We compare continuous representation learning and PSM building versus continuous representation learning only and LSTM. The overall system throughput is still quite high, even with PSM building. We can see that throughput of our model training is over 2 orders of magnitude higher than that of the LSTM model. This is expected as the training of a deep learning model is much more computational expensive and is indeed one of our motivations for using a multi-relational graph representation learning method with significantly less overhead for real-time fast streams. Figure 11 and 12 show the overall throughput of combining continuous representation learning and continuous PSM learning is still quite high by using different sample size. We then study the selection of the number of clusters states in the PSM, and the results shows in figures 13 and 14. Figures 15 and 16 show that we can nicely monitor and foresee the critical events by observing the fluctuation of the overall cost value. We can see that the accuracy of our PSM model is competitive with or slightly worse than the LSTM model. However, the throughput of our model training is over 2 orders of magnitude higher than that of the LSTM model. Furthermore, interestingly, also the clustering of states is based on the latent features in the embedding vectors. We find that the resulting states have a distinctive semantics and interpretation. For example, in the hospital dataset, we find that treatment code and diagnosis attributes are more important than the edge attribute. The interpretable pattern structure of a PSM is one of the major differentiators from a deep learning model. We cannot find any common pattern for the critical events in all 3 datasets by using L-manner because it requires strictly common pattern. By contrast, our pattern language is stochastic and much more flexible and powerful. For conclusion, we study a novel problem, which is to discover subtle and complex event patterns paired to critical events from the training data stream. We resort to a representation learning approach by first transforming an arbitrary multi-stream to a dynamic knowledge graph. We then devise a novel embedding algorithm using the attention mechanism and embedding pooling aggregation. Moreover, we propose algorithms to learn the probabilistic state motion patterns and a causal model to use them to monitor the imminence of critical events, as well as to choose the optimal parameter of the pattern model itself. Our extensive experiments demonstrated the effectiveness and advantages of our method over previous work. Thank you.